This was a program that was emailed to me, and it's not working right. So I'm gonna take a look at it first part of class, give people a little bit extra time to get here if they're not here because of the cold. Okay. So build and run. Gallons used, miles per gallon. So miles, okay, so 10 gallons, then 40. Okay, that's right. 20 and 3 miles. I don't know if that's right or not. 3 and 20. -1. Oh, the overall maybe is what the question was about. Should have brought in the question too. Let me check the overall average. Okay, so we got a total. That's presumably our total miles. I've seen somebody else do this. I would not count it wrong, what I received here. I think what they meant for you to do is add up the total miles, total gallons, then divide those. Not take your total, not average your miles per gallon each time and then divide by the counter. Question is if it gives you the same math value. Well, let's see. Total miles equals 0. Oops, wrong place. Total miles equals total miles plus miles. Float total miles, total gallons. Oh. Now set total gallons equal to 0. Gotta put that inside here. Total gallons equals total gallons plus gallons. And the question is, did I get the same result? The overall average miles per gallon was %6F/N, and then total miles per gallon. Okay, total miles divided by total gallons. Okay, so let's run that.
Total files.
Total files. Yeah, that won't work, will it? Okay. And I don't know the answer to this myself, and it isn't like something else. Oh, semicolon. Little red square, of course, indicates where you have an error. Okay, so let me see. Miles per gallon. Miles should be the bigger one. 40, 20, 80, 20. Wait a minute. Miles. Okay, 3 and then 20. This is actually your average miles per gallon. This is the average of your average miles per gallon. So, but if you calculate it either way, I'd take it. That's part of when you go out and work in the workforce, you would give it to them and hopefully ask them the question, is the numbers right? And they would actually look at it and say, no, I think you calculated this wrong. And then you'd go back and do that. Because otherwise, every computer programmer would also have to have a degree in accounting, they'd have to have a degree in engineering, degree in any field where they're programming. Okay, let me get my PowerPoint out now. This is chapter 4, C, program control. And it's some more repetition structures, more controlling the flow of the program. And I think there's also the math library introduced in here. There's some other items too. Okay. We already talked a little bit about sentinel controlled repetition. This talks about counter controlled repetition. That's where you're going to control how many times you're going to do something. You go through it 10 times, go through it 20 times. Unlike the previous chapter where you go through it however many until they enter -1 to quit. I'll focus on the for loop, but if there's an example on the PowerPoint, I'll talk about the do while. I don't like the do while. Switches I don't normally like. In 13 years of programming, I only had to ever use switch one time. And I probably mentioned that, but I'm getting old, so I'll mention it again. We were programming something, the product flow on the production floor. And they had barcodes that they would put on their PCB boards. And they'd come up to the little workstation we had. It was a diskless workstation. And they would scan in what they were doing. They had a sheet. They could scan in that they were submitting work to a work order. That they were, it's been too long, that's the only one I remember. But they'd come up there, they'd scan the work order number. And it started with .wo. They would scan the sequence, .sq. Quantity we didn't have a code on. But this barcode here had a code on the front. The reason why they told us this, they said we want a code on the front. And they said otherwise people are going to be going up and they'll be scanning their pop bottles on a production floor. Well, we had so many codes in there that it was just easier to handle it with a switch statement, a case statement. But other than that, I've never done so many if-else statements that I actually needed that switch. Break and continue, I don't really like. I probably can just skip over them, not even talk about them. I think break and continue are necessary if you don't know how to program. So you don't know how to do a while loop, you don't know how to do a for loop. You use these to break out of them ungracefully. So you don't let it complete its natural cycle that you designed in the first place. You break it in the middle. And I can see where there might be places where you'd want to do that. But okay, so there's our chapters. Let me go down. Here's an example of a counter-controlled repetition where we set the counter equal to 1. We continue while counter is less than or equal to something. And then we're going to increase our counter in some form. Well, let's see what in the world I'm talking about there. And I'll use their unsigned integer, x. And I'll set that equal to 1 initially. Now, I want to add up all the numbers from 1 to 10. I think we did a similar example of that last time. Now let me multiply all the numbers from 1 to 10. Be a little bit different. Product is equal to 1. And I'm going to have a while. And then I'll say that my x is less than or equal to 10. Then I'll say product is equal to product times x. And then x is equal to x plus 1. So I got printf. A product is %d for decimal integer, /n for the next line, comma, and then my product. Now, I don't know what all the numbers multiplied from 1 to 10 is equal, so that's probably not a good choice. I'm going to temporarily change this to 3. because I know what that is. 1 times 2 times 3 gives me 6. So let me run that. Product is 6. So now that I've done a simpler test, I can change that to a larger number. And it's interesting. Well, numbers multiplied from 1 to 10 gives you 3,628,800. I guess that would be right. Because if you have taken math classes, if you remember factorial, 3 factorial, 1 times 2 times 3, and they very quickly become huge. So now initialization. That's where you're setting it equal to an initial value. So that's our initialization right there. We're repetition condition. This is where we're checking. We're going to continue this loop over and over while this is true. So every time x is less than or equal to 10, we're going to continue this loop. And then the increment or decrement, whatever you're doing. This is going to increment it by 1. Now, there's a lot of places you can go wrong with a while loop. Some of them I may have mentioned last time. I'm a little bit braver tonight, maybe because I'm sick. And, I just started class. Putting a semicolon here is one of the worst things you can do. If I run that, it's nothing. And you can sit there and wait forever. It's never coming, well, I shouldn't say never comes back. It'll probably bomb off at some point. The reason why is when you put a semicolon right here, it's coming down, x is equal to 1. It's checking, okay, is 1 less than or equal to 10? It is. So it'll do everything between the end of this parentheses and that semicolon. And there's nothing there. So then it comes back and it checks this condition again. Then it checks this condition again. Checks this condition again, one gazillion times till it finally eats up enough memory where it bombs off. That's an infinite loop. A good IDE, a good programming language, in my opinion, does not allow you to put a semicolon there. You would never put a semicolon there because there's never a time when that would actually work. Okay, the other one is this right here. If you don't have it being increased. So now if I run this, again, it's never going to come back. Because x is always equal to 1. Comes down here, checks, is 1 less than or equal to 10? Yeah, it is. So it takes my old product times 1. 1 times 1 times 1 times 1. So yeah, it'll continue forever. So have to have those 3 components. Have to have your initialization of some sort. You have to have your check on your condition. Do you stop or not? And you have to have your increasing, decreasing statement on your counter variable. Now they put a plus here. I don't really use those. Not in a while loop. I don't even know what that's doing, to be honest. No clue. Where you would really see it at is not there. Let me do a printf here. X is equal to %d / n x. I'll get rid of that line. Okay, so if I ran this, it starts at 2 and goes to 11. Whether you put the plus before or after the x decides when it gets incremented. And I think it, like this plus here, increments it after Yeah. Well, no. I don't like think that hard, so I don't do these things. If I put the plus plus there, goes 2 to 10. Do you see how it just makes your life harder? It's just like, why bother? Put x equals x plus 1 down here. It's not too hard. Keep it simple. Then you don't have to think as hard. And unless you just like mental challenges. If I run that, it goes from 1 to 10 like I'd expect. I talk about the Perl program in here. P-E-R-L. No? They didn't do it very often. And probably after the way I butchered it, they would never did it again. But usually the engineers, electrical engineers at IFR, they considered the regular programmers kind of like play programmers. We weren't doing real programming. And probably compared to some of their in-depth programming, because now that I'm teaching assembly language and all this and that, they have some pretty complicated programming. But again, there was a difference in the programmers there. One time they asked me to come out because the electrical engineer that had written the program originally was working on a project that had to be out, had a heavy due date on it and so forth. And so they took me out to work on one of his Perl programs, and that's P-E-R-L. And he had written it with all these clever little programming techniques. And I'm sitting there, and he had there was no nice variables called product. There's P. Variables called P and X and Z. And I'm sitting here, and I could easily probably spend a year trying to figure out what in the world he was doing. So I was just kind of out there killing time, waiting until death took me or they gave up. After 2 hours, they gave up, and they told me to go back. They could tell I wasn't going anywhere. I don't know what they ended up doing. Keep it simple. Okay, that shows that. Got our counter. Here's a plus plus. Let's see what in the world that says. Increments the loop counter by 1 each time the loop is performed. I think you get the same result if we put a plus plus after it. For example, here, instead of doing the x equals x plus 1, let's do x plus plus. 1 through 10. Let's put a plus plus here. I don't even know if you can put it in both places. 1 through 10. So whether it's in front or behind doesn't matter if it's the only thing on the line. Let's see. Skip over this. Oh, good programming. Let me talk about those. Let's see. Common program. Floating point values may be approximate, so controlling counting loops with floating point variables may result in imprecise counter values and inaccurate termination tests. What they're saying here is you do not want to declare x as a float. If I run it, well, if I change my %d to percent, what was it, f? You see there's no difference here. But error pops up if you have certain calculations go up to certain numbers, so they say don't use those. And there's really no need to, because float just takes up more memory. So if you can accomplish the same task with an integer, you should. Even though if you're going into the computer science and you're going to be programming just computers, and they got tons of memory, you still shouldn't be sloppy with your memory. Let's see, control counting loops with integer values. Yeah, that's always a good idea. Too many levels of nesting can make a program difficult to understand. As a rule, try to avoid using more than 3 levels of nesting. What in the world does that mean? I can't think of an example where I could actually use that. Okay, Pythagorean theorem. That's bad. Can't spell Pythagorean. Okay, I'm not going to give up that easy. Pythagorean theorem. No spell. Pythagorean. There we go. Just have to type it real fast. Remember that's a squared plus b squared equals c squared. I could write a program that would give me all the Pythagorean, what do they call it, triples? All the numbers that work, like 3 squared plus 4 squared equals 5 squared. Let's see. Except for we haven't covered the for loop, and I hate to do this a while. But since I started, a is equal to 1, b is equal to 1, c is equal to 1. And I'm going to not use the for loop. Say while a is less than or equal to 300, while b is less than or equal to 300, while c is less than or equal to 300. So I'm gonna change these each of these by 1 each time through the loop. So here I'll say c is equal to c plus 1. And I'll do a check if a times a plus b times b equals c times c. Then I'll print out the numbers. If a times a plus c times c equals b times b, I'll print out the numbers. And if b times b plus c times c equals a times a, I'll print out the numbers. A, B, C. Okay, so this is increasing C. Here I want to increase B. Or do I? Let me think. Yeah. B is equal to B. This is a lot easier, the for loop. When I get down here, I want to set C equal to 1. Don't worry about this example. It's kind of a lot more complicated than I thought when I started. Unless you're really into math. Of course, it'd be questionable whether I get it right or not. Let's see. C is equal to 1 here, so I'm guessing this has to be B equals 1. And let's see if I have an infinite loop. That can't be right. I think it's finding every number, isn't it? Well, maybe it is. 3, 4, 5, 3, 5, 4, 4, 3, 5. That looks good. Gosh, there is quite a few Pythagorean triples. Now we had duplicates. How you can get around that, if you're into math, is if you assume A is always going to be your smallest number. Then, let's see if I remember how to do this efficiently. Okay, if I assume A is going to be my smallest number, B is my next one, then I can simply put else's on here. Oops, not there. Else and else. Nah, that's not going to work. Oh well, it's not going to come to me, so I'll forget that idea. But there are plenty, including duplicates. This is what we're talking about. Too many levels of nesting can make a program difficult to understand. You'll find with the for loop, it simplifies this quite a bit, but don't use more than 3 levels of nesting. I'm assuming that's what they mean by nesting. Combination of vertical spacing before and after control statements and indentation of the bodies improves a two-dimensional appearance, or gives programs a two-dimensional appearance, greatly improves program readability. So use spaces. Make sure things line up. Just like right here. Now, some of these IDEs do that for you, but it helps you to see them. Like if I did not put the spacing here, I would not know where this really belonged. It came to me. C is equal to B, B is equal to A, I think. Let's see. Yeah, that was it. It's because I don't start C back over at 1. I started at the previous value of B. And a Pythagorean triple can never all be the same. You can't have 3, 3, 3. Okay, now here's the one that's preferable to use if you can. Sometimes you have to use a while loop, because maybe you want the total control. Maybe you don't know when you're going to stop, like those Sentinel controlled ones. A for loop has all of it contained within one line. You got your initialization, you got your check, and you got your increasing or decreasing, whatever the case might be. So, for example, here I found all the Pythagorean triples, and it was pretty clumsy. Instead of doing it that way, I could say for for int a equals 1, continue while a is less than or equal to 300. I forget what I had. And a plus plus. And for int b is equal to a, continue while b is less than or equal to 300, b plus plus. For int c is equal to 1, except for I don't want b is equal to 1, or do I? B is equal to a, and c is equal to b. And then I'll continue while c is less than or equal to 300 and c plus plus. And if that's true, I need my if statement here. If a times a plus b times b equals c times c, then I'll print off my values. that's not right. 2, 3, and 4. What did I do wrong? Oh. Let's try that again. Three, 4, 5, 5, 12, 13. Okay. Does that look cleaner than the other one? While loops are nice. They give you a lot of power, but you have to have 3 separate lines where this has 1 line to control the flow of the looping. Now we're gonna look at a lot easier examples than that. Let's look at multiplying the numbers from 1 to 10 like we did before. Okay, I set product equal to 1. For int x equals 1, continue while x is less than or equal to 10, and x plus plus. Product is equal to product times x. And then printf, the product is %d/n, and then product. Now let me run it before I explain it. That looks like what we had before. Okay, I set product equal to 1. Then I come down here. It sets x equal to 1 initially. It's checking if this right here, it's saying, hey, is x still less than or equal to 10? And it is, x is equal to 1. So it comes down here and runs this line of code. I don't have curly braces around it because I only have 1 line of code. You never need the curly braces if you just got 1 line of code. It doesn't hurt. I could put my curly braces there. So that doesn't hurt anything. But it comes down here and multiply these together. So the old value of product, which is 1, times x, which is 1. 1 times 1 is 1, and assigns it to product. Comes back up here. This is only done when it first goes in the loop, so it never does that again. This increases it by 1. So x is now equal to 2. It checks. Is it less than or equal to 10? It is. So it comes down here and does this. Comes down here again, increases x by 1, and so forth. Now, if you're not sure the order, like does it do this first or this first, you can put a printf statement here to print out the values of x, and that'll tell you. X is %d/n x. X is 1 through 10. This would be different if you did the plus plus here. I think it, I don't know what it does. Let's try it. Same thing. Okay, well, never mind. I guess you can put it anywhere you want. Never affects it. Now, what you can do is you can do x is equal to x plus 1. Same as when we had in the while loop. So instead of doing x plus plus, you can do that. Now, typically, if you're programming a for loop, people always put x plus plus. I don't know why, but it's just standard there. Now, the while is probably 50% people will put the plus plus, 50% won't. No. It's just whatever helps you to understand it. The benefit of writing it this way in class, though, is I can show you don't have to increase it just by ones. I can put a 2 here, so it increases it by 2s. Start at 1, 3, 5, 7, 9. Next one is 11, which is greater than 10. So it didn't do that one. You can do whatever calculation in here you want. I can take x times 2 divided by x. That's probably an infinite loop. I don't know. Minus 7. Because remember, these are all integers. I don't know. Let's try that. Looks like an infinite loop to me. Because x is 1. 1 times 2 is 2. Then 2 divided by x. 2 divided by 1 is 2. Minus 7 is -5 always. Yeah, that wasn't a very good example, was it? Right. But this just demonstrates you can put any formula here. You tend to see this so much that you always just put the plus plus. But you can put anything there. Let's see. Now, if you want to look at this PowerPoint closer, you can just email me and I'll send it to you. Or put it on Blackboard. Here's the off by 1 errors. This is where you're not sure, should this be less than or equal to 10 or should it be less than 10? Again, a good way to do that is keep your looping small and print out the value. That'll tell you whether you got all the ones you wanted. Then you can get rid of that after you're done. Error prevention. Using the final value in a condition of a while or for statement, using a less than or equal to relational operator can help avoid off by 1 errors. For a loop used to print the values 1 and 10, for example, loop continuation condition should be counter is less than or equal to 10, rather than counter is less than 11 or counter is less than 10. Not sure if I agree with that necessarily, but using commas instead of semicolons in a for header is a syntax error. You notice when I did this here, I put semicolons between them, not commas. So they're just saying you can't put commas here. Placing a semicolon immediately to the right of a for header makes the body of that for statement an empty statement. There's normally a logic error. Logic error. I guess that would be a logic error. It's an infinite loop. Remember how we put the semicolon at the end of the while? Putting a semicolon here, well, no, it won't. I'm lying. That's not an infinite loop. It'll go through here, and it'll increase x each time, and it'll just do this one time. It'll just do this when x is equal to 10 or 11. Let's see. Maybe. Did I click it? Doesn't like that. What in the world did I do? X is %d. If, well, they're half right. They say it's a logic error. Logic error means your logic's bad. It runs. This is actually a syntax error. Reason why is when you put a semicolon here, x is only defined up here. It's not defined where you can access it here. So I'd have to get rid of any reference to x for it to even get past the syntax error. Product is 1. But anyway, can't have a semicolon there. First time you spend 2 or 3 hours, days, looking for that extra semicolon you put at the end of a for or while, you'll never do it again. Or if you'll look for it pretty fast, because you can sit there for hours and hours trying to figure it out, and then it hits you. It's like, oh, shouldn't be a semicolon there. And I think this is showing you can have all kinds of different formulas, like I was indicating. Although the value of a control variable can be changed in the body of a for loop, this can lead to subtle errors. It's best not to change it. That's a bad programming practice. If I have X controlled all up here, then down here you do not change the value of X. 2, 4, 6, 8, 10. If I wanted to go 2, 4, 6, 8, 10, what should I change up here? What would this go start at? 2. So I want to start at 2, right? And then I'm going 4, 6, 8, 10. So I'm increasing it by 2. Never, never do that where you're changing the value of your variable within your loop. You might say, well, why? It achieves the same result. When you're a programmer, you're looking at somebody else's code, you're assuming this controls everything. That's the idea of a for loop. It's completely controlled by this. You do not change the values of X down here. Nothing. Although statements preceding a for although statements preceding a for and statements in the body of a for can often be merged into the for header, avoid doing so because it makes the program more difficult to read. I don't think I've ever seen that in my entire life. Almost implies you can take this and put it up here. I'm sure that's not what they mean. See if you can even do that. No? I don't know. Limit the size of a control statement headers to a single line if possible. Again, try to keep this all in one line, keep it short. Notice I used the variable X. I just was cursing that electrical engineer out earlier saying he used X and P and single letter variables all over the place. When you got a variable that's controlling your loop, oftentimes you just use a single letter. You don't have to. Sometimes I use X, sometimes I use index. This is an example. What it wants to do. Okay, got this. This program involves a loop that performs indicated calculation for each of the 10 years the money remains on deposit. Okay, so let's program this. For int x equals 1, continue while x is less than or equal to 10, x plus plus. This would account for our 10 years. Although a better variable than x, year 1, year 2, year 3, so forth. X would have worked just fine, but this probably self-documents, doesn't it? Now, we need to, I guess, ask the user for P for principal and R for rate. In.
We forgot to change the X to years.
It'd still be right. Yeah. Yeah, they got in as a number of years, don't they? So probably to match the formula a little bit better, let's put in there. N. What in the world?
Would be a number. That's weird.
Yeah, I've taught college algebra for 24 years. This is my first semester in like 24 years. I haven't taught college algebra, and it's A is equal to P times 1 plus R over N to the NT power. T is always your number of years. N is the number of times compounded per year, and but I'm not a business major, so maybe this formula is used. But anyway, we'll go with that. Okay, now first I guess I need to ask him for principal. Input principal. How do you spell principal? Think like that. Free float principal. I need to ask for rate. I guess that's it. Okay. So scanf. Was it percent F? And then at principal printf input rate scanf percent F rate. I may have to look up that syntax. Why does it tell me to have an error? N equals 1, continue while n is less than or equal to 10, n plus plus. Now, welcome back, Dad. Maybe it's because I haven't put any code in there yet. Up here, they show where we can include something called a math.h. This is where you can bring in libraries. Now, as I start typing, these are all the ones you can bring in. And we're going to use some math libraries, so that's why they're having us import the math.h. And I guess I also need the amount. So here I'm going to say amount is equal to principal times P times 1 plus R. So 1 plus R, which is rate. I guess I should have used R, but oh well. Now we need the power here. And that's where that math library comes in. There's a POW function. And I may not get this right the first time. POW. 1 plus rate, comma, n. And then I'll print the amount is percent dot 2f slash n amount. Good part about being sick is I can blame me not finding an error on being ill. Not sure if you'll buy that, but I can blame it on that. What in the world is wrong with this? Maybe it'll run. Let's see. Why did it run? Because there truly is no error? I don't think it'll work anyway. because I'm mixing some variable types in here. N is an integer, and I'm guessing I'm going to have to change N to a float for it to work right, but let's see. 1,000 for my principal, rate is 0.04. I don't know if I need 0 there. And I get some kind of values. I have no clue if they're right. Raising it to a power, N. So N is 1 to begin with, okay. 1 plus rate. Rate is that, so 1 plus 0.04 is 1.04. 1.04 times 1,000. Yeah, that's right. Okay. And my little red square is gone. What I expected is that this would not take it because it was an integer. I fully expected to have to cast that by putting a float in front of it like that. But I didn't. So. Is there any questions on that that example? Now I might make it a little bit more user-friendly. I might say year percent D colon, and then I might put the N in here. So when it did run, I would see which year. 1,000, 0.04. You see year 1 through year 10 tells you your amounts. Change it to 100 years. I'm going to leave it in 100 years and see how much money I have in my account after I'm done. It's 1,000, 0.04. So if I put 1,000 in, I don't have to deposit any more. After 100 years, it'll be 50,000 in the account, more or less. If I leave it there for 1,000 years, and then I go see how much I have in there. Let's see, comma here, comma here. I don't know, what was that? Like $1 gazillion? At this point, my family's got enough money to buy planet Earth. I'm the new Koch brothers. We're so rich, we don't know what to do with it. Yeah, that was always my dream. Put $1,000 in a bank account and pass that bank book from generation to generation. 1,000 years from now, we own the planet. But there's a problem with that. They don't let you do that. You got to have activity in your account. You're assuming your family line's not going to die out at some point, and plus they put limits on it. But this shows you the power of exponential growth. So if you've ever taken college algebra, it's kind of fun. I always show that in college algebra, though not with programming. How does my code compare to theirs? Principal times POW 1.0. That's interesting. They do that 1.0 to force it to be a floating point value plus a rate. But if rate is already floating point, you shouldn't have to do the 1.0. And then comma year. And they use year up here. They don't declare it. See how there's no declaration in front of the year equals 1? They don't say whether it's an integer or a float. Let's see what they said it as. Unsigned integer year. So you see, you don't have to declare it right within the for loop. It's easy to, but you don't have to. Okay. Remember the POW function? I said I didn't think it'd work, but it did work. It says it takes 2 arguments of type double and returns a double value. I had n as an integer. So that's why I didn't think it'd work really. Hmm. Notice we defined the variables amount, principal, and rate to be of type double. We did this for simplicity because we're dealing with fractional parts of dollars. So do not use variables of type float or double to perform monetary calculations. The impreciseness of floating point numbers can cause errors that will result in incorrect monetary values.
I have a question.
Yeah.
You're not supposed to use float for money. What are you supposed to use?
That's what I was just sitting there thinking. Well, what else is there? I mean, I know there's a larger, like float or double, but I think it still would have the same imprecision with it. Yeah, they say that you can use integers, and I don't think so.
You wouldn't have a period though with an integer.
Yeah, to use integers, I think would be kind of a challenge. Huh? I don't know.
I guess you could have separate variables for your dollars and cents, and then just print a period in between.
Well, see, I've seen this in programming, where you got like num1 is equal to 3.14, and num2 is equal to 4.57. Then what you do is what in the world do you do? You can multiply num1 times 100. Now, when you multiply it times 100, it'll move the decimal point 2 places to the right, and it's no longer 3.14, it's 314. But num1 is a float. Float times 100 is still a float. So I'd need to do a cast, and I think int here. Might have that wrong. We'll see. And then I could do the same thing for num2. Now both of those are integers, and I haven't lost any precision. So my product I can say my product is equal to I num1 times I num2. And then printf the product is %.4f/n, and I'll cast product to be a float, so that changes it to a float. Divide, let me see, I multiply by 100, so I divide by 10,000. Three times 4, that's roughly 14, I'm assuming. So you can convert them to an integer, but you have to do a lot of thought process on it to do it. I've never had a book tell me I shouldn't use float or double to perform monetary calculations, unless I mean a higher precision variable type. But maybe they'll cover that. Two float, which is added, they produce a sum, which is they're all messed up if that's the real reasoning. what they're implying is that we bring in two amounts with 3 decimal places, but we only print it with a dot 2. So we only print 2 decimal places, which means we'd have 14.23 and 18.67. And if you add those together, it does not give you this, which is actually taking 3 digits, adding together. A better way, and I'm pretty sure it's in the math library. Let's see if I'm lying. Num1 rounded is percent dot percent f slash n round num1 I might be remembering this wrong. Why is there a red squiggly under it? Num1 rounded equals round num1 rounded. Okay, so I'm not remembering the round function correctly. Maybe there isn't a round function in math.h. Round. And do the next find. Find next F3. Round. Using FPU control word settings. Okay, I'll give up on that. Save changes, no.
So why would a float be imprecise in the first place?
Why would it be imprecise? Should be able to tell you that. I taught the introduction to digital design last semester. I don't know. Integer. That returns an integer. So rounding. Okay. I don't want it to return the nearest integer. Rounding floats, doubles, something. That's too hard. Huh. I don't know. I don't have a good question for that, or a good answer. Typically what you can do is if you want to round it to 2 decimal places, then if you take your original number, you multiply it times 100, num1 would be a float times 100. No, that shouldn't have to be an integer there. I don't know. I'll come back to that because I'm not remembering the exact syntax. Just the general idea is if there isn't a function for rounding floats, if I have this, if I round at 2 decimal places, what should it be? Yeah, so it'd be 3.15. From a programming standpoint, if you don't have a round function, some programming languages don't have it. If you take this and you multiply it times 100, 100 moves at 2 decimal places. Then this would give you 314.6. Now, if you have a round function for integers, as they implied that one web page, then if I round this based upon integers, then it would give me 315. And then at that point, you take your 315 and you divide by 100, and that gives you your 3.15. Now you have to do a little bit more tricky stuff if you have no rounding at all. But that one web page implied that we had a rounding function for integers. But I'm sure they'll get to that someday. Okay, you've been warned. Formatting, we've already looked at the precision on that. You see here the minus sign is used to left justify integers. So if you want integers aligned on the left, then you do that. And character strings. Now character strings can become important. So let's talk about that. If I got, oh, we really haven't even talked about strings yet. I wonder why they mentioned that. Never mind. I'm going to cover that after we cover strings in the course. They're looking ahead. Okay, the switch statement. This is, let's see, where's it at? Put S, enter the letter grade, put S into, enter the end of file character to end input. Put string is what that's referring to. See how it prints those? No different in this case, except for this is line 2/n. You see it gives you the same result. The benefit of this is that this makes it a little bit more flexible in future programs. We'll see that, why you'd use that. Now, we have the get char here. What this does is it gets a character, a single letter, single digit, single something from the user. So if I have a while statement here, and integer grade, and we're going to check while grade equals get character, not equal to end of file. Let's see if I can remember the format specifier for a character. I was thinking C, but it might be D. We'll see if that works. So what I'm doing is this get character here is getting a single character. It's waiting for me. It's saying, okay, I'm waiting for a character. You type in a single character, and then it checks to see if it's the end of file, which I think is Control C. We'll try that here in a minute. And if it's not the end of file, it prints it. So now if I do a Control C, went away. I wonder if that, yeah. Huh, I expected I guess I don't have any printfs in there, so it didn't print anything. That would be like if you're taking this a character at a time. And so you scan that in, and it sends it a character, sends it another character, sends it another character. And even though it's a real long string of characters, it's still the same idea. Now, I don't, sometimes you have to program it special. See how I typed ABC? So I don't have to put a single character in. So if I had a scanner here, I could scan my barcode. It would put each one of those as a separate character. This is where in my program at Control C, program at IFR, I had them scan in their entire barcode like this. And this is just standard code, by the way. I didn't use it very much, so I always have to look it up. But at this point, then you want to check what they input in. For example, and I'll look up this syntax because I don't got this memorized either. Switch, then grade. Switch, grade. Beginning curly brace. And this says case. And single quote. If I put a dot there, this is what in a production floor they had to start all of our barcodes with. Had to start with a dot. That would tell you that it's a valid barcode versus something they're trying to scan in like a pop can. So with this case here, we're going to do some code. And then you have a break here to end that condition. And maybe this code might be to indicate that it's a flag is equal to 1. What the flag might tell me one, two, three. I don't got enough spaces there. That's bad. This flag equals 1 tells me it's a valid barcode. So I'm setting a valid barcode there. Okay, so if they do a dot, it sets that flag. Then I do a break. If the next one was like a W for work order, .wo is what the work order was. Well, then in my code here, I would check if flag is equal to 1. That means that the previous character was a dot. And so I know how to handle it. So I'd handle it appropriate. Accumulate. If my, and this is where you could have a bunch of if statements within a switch statement. But if the next one was an O, well, this would be assuming that my previous one was a W. So I might check to see if there's a flag indicating the first one is a W, or what was the last character. For example, I could keep track of last character, and here, if it's a W, then I say the last character equals W. I need a break there. It took a little bit to get the code right on that, such that it'd work. But it was pretty slick afterwards, because I didn't have to have a gazillion if statements to handle all the different cases we had to come up with. And it actually came in from a scanner, a character at a time. So I couldn't read it as a string. I couldn't say, okay, if it's equal to .wo. It was, okay, if the first character is a dot, if the second character is a W, if the third character is an O, then all the rest of the characters will be my work order number. So anyway, I'm not going to just type in the example they have. But what they're doing is they're asking if the person's entering an A. If they are, they're increasing A count. If they're entering a B, they increase B count all the way to F. This counts how many grades there are of each type. Then down here, I assume they print them. Yeah, then they print the counts. They use %u for the unsigned integer. Yeah. So that's the format specifier for the unsigned integer, %u. Although I think we've been using %d, and I think it's been working. Does anything bother you here? The what? Int? Yeah. Because int is what? A number with no decimal, right? And we're checking it against letters. It's like, what in the world? It has to do with how it looks that up. Let's see if I can get to the web page here. That's not it. Table. There's a website for ASCII table. When you're talking about a single letter, that single letter can be translated into a integer. And so that's what's happening with that. Because we're free form, we declare an integer, but then we checked it against D or M or so forth. So it's actually doing a translation for you on that. So, and interestingly enough, although we're not going to write any libraries on that, if you look at the difference between, what do we look at the difference between? I don't want to work hard. P. Uppercase P here is 120. Lowercase p is, wait a minute, I'm looking at the wrong one. Helps if we look at the decimal. Okay, uppercase P is 80. Lowercase p is 112, which is a difference of 32, isn't it? If you look at the difference between uppercase A, which is 65, and lowercase a, it's 97, which is also what? 32. That's how you can switch something from uppercase to lowercase, by adding that to that character. Since it's just an integer, isn't it? Oops, cancel. Usually I don't do that. I use the program's functions in order to convert it, but you can do that. Shoot, we're going to go about an hour and a half, haven't we? Well, let's go ahead and take a break there. We'll start again in 10 minutes. Start at 8:35. Grab my coat. Is it cold in here? round F. And three. That's not right. N1, that times 100. That should give me 314.5. Number is an integer. Ah. $3.15. Here's how you could round. I did a search to see if I could find if there was a function for rounding in math.h, and I couldn't find anything. But I did find roundf, which rounds a floating point to the nearest number, appears like, nearest integer. So if you have your number, you multiply it times 100. Why do you multiply it times 100? Because you're rounding to 2 decimal places. If you're rounding 3 decimal places, you multiply by 1,000 and so forth. So then that would give us 314.5. Round F would round just like normal, so that gives us 315. And then going backwards, divided by 100 gives you 3.15. Most programming languages have some kind of rounding function, so you don't have to worry about that. But if they don't, that's how you can write your own. And it works. It works just fine. I don't think there's any situation I could think of where it doesn't work in terms of that. You just have to. What do you have to do? Number of rounding, or number of places rounded to. Let's say that's equal to 2. You don't want to sit there and hard code necessarily 100 and so forth. So you'd have a for loop, int x equals 1, continue while x is less than or equal to number of places, x plus plus. And if I called it factor, let me call it something that's meaningful, power of 10. If I had the power of 10 equals 1, power often. So then I'd have my power of 10 equals power of 10 times 10. So if they wanted it rounded to the number of decimal places, and you could ask the person this in your program, how many places do you want to round it to? And if they said 2, then this would automatically loop through, and x equals 1 initially, and it takes power of 10, which is 1, times 10, which is 10. And then second time through the for loop, 10 times 10 is 100. So instead of hard coding this, you could put power often, power often, like that. So if you had something like that, and you'd ask them how many decimal places, scanf %d, and then number of places. Then one hard code it there. So if I ran this now, if I said 3 decimal places, 3.146. If I ran this and said 5 decimal places, 5, 1, 2, 3, 4, 5, so 1.14589, and so it works. Even more than that is on my printing down here. Oh, how could I do this different? I have to think about that. I could put a bunch of if statements, but make sure it prints to however many places I want to round it to. Is there any questions on that code? This talks about testing for the symbolic constant EOF rather than -1 makes programs more portable. The C standard states that EOF is a negative integral value, but not necessarily -1. Thus, EOF could have different values on different systems. So if you're running this on Linux, you're running it on a Mac, you're running it on Windows, running on whatever, your end of file may indicate -1, -2, -3. So they just specify this symbolic constant. A constant is a number that doesn't change, like pi. And see, I got math.h here in code blocks. If I right click on that, I can say view the header footer. Oh, open the math.h. And these are all the different things that you can access. Here's like mathematical E, 2.71, all those decimal places. So if you've taken algebra, calculus, that's like, the E from the interest formula. That's strange. I don't know why log base 2 is important, but there it is. And here's log base 10, natural log 2. I wonder what that means. Maybe the 2 isn't what I think. pi, of course, that's a real obvious one. So these are things you can access within your program. If you scroll down, these, for the most part, in here there's constants, of course, but there's mainly just definitions. Not necessarily code, but it's defining. Like, I think that's a math function. Arc hyperbolic cosine? I don't know. It's been too long since I. But they got a lot of different options in here. What was it? Oh, so maybe it's. Yeah, that's sad. I'm starting to forget some of that stuff. Okay. This says on Linux you do Control D to do the in a file. I did Control C, but this indicates Control Z. That's interesting. You may also need to press Enter on Windows. Break. Let's see. Common programming error: forgetting a break statement once needed in a switch statement is a logic error. The default case. So if none of the above is true, it does the default. Default should be last. Good programming. Break statement isn't required on the last element. Here's an example of ignoring new line, tab, and blank characters in input. So you can check for case of /n/t and I guess a space. And then you just do a break. There's no code at all. That just ignores those. So it cleans out those invisible characters. I doubt if I can spot it, unless it actually says it. Remember a horizontal tab that we looked at? /t. That's this here. Carriage return. There's a carriage return, and then there's another one too. I'm probably looking right at it. Line feed. Line feed is a /n, and I have no clue what carriage return is. You see this in packages. Sometimes you have to write programs to handle that appropriately. Hi, how are you doing? I am fine. Hope everything is going well. Do you notice some differences there? See the spacing between these two is a little bit more than this. Might not even hardly be noticeable. If I did the paragraph mark here, this was a carriage return. When I press carriage return, it puts that invisible character in there. When I was right here, I did a shift enter. And shift enter puts the line return on there. This which one is it? The line feed right here, the new line. That's your /in, and packages will put that in there. And the inner by itself is your carriage return. Well, why is that important? Well, the paragraph mark, it looks horrible when you look at a web page. Puts a lot of extra space in there, a lot of extra white space. If you just do a shift enter, it puts your text closer together. I've worked before where the users create their web pages using Word, because everybody has Word. So it's and most of your documents are in Word. So put those in a web page is fine. Well, then I got the request, well, our web pages look horrible. We've got a lot of extra white space. People are complaining when they print because it prints 10 extra pages because of all that white space. You can write a program to go through and replace all of these carriage returns, paragraph marks, as line feeds. So, and then when you save it as HTML, it looks a lot better. So, anyway, sometimes in programming you have to worry about that. Sometimes you put the codes in there. At IFR, we had this printer, a Zebra printer. It was a barcode label, or not barcode, for the serial numbers that go on the back of the spectrum analyzers. And it was special labels. And print the serial number and print other information about that spectrum analyzer. We used to send it out and had somebody print these metal plates. And we attached the metal plate to the back of the spectrum analyzer. That was expensive. We had to wait for them to print them and so forth, and just took a while. They wanted to print it themselves. So we got this. And the labels were special. If you peeled them off, they left bits and pieces on the device. Because what happens if you open up a machine? In some cases, void the warranty. So by leaving parts of it there, you can tell if somebody's stripped that off, if you put it in the right place. So that was one of the purposes. The other purpose is if you peel off the label and put it on an older machine, well, it can look like it's under warranty when it's not. So that was the two things they wanted. But we had to pass in special characters. So it would print a barcode and do this and that. I hated that. That program. That was one of them I worked on, and it just took forever to figure out what it needed. Even though the manual for that printer said it just took a lot of playing. And the one I didn't work on, and this is before everybody's time, but there used to be a printer called a dot matrix printer. And it was the same way. You had to send special printer codes to get it to do those special characters. And like I say, I didn't write that original program, but I hated that. I hated that program because I'd have to go and fix it. my manager, she wrote it, and she did a good job. Don't get me wrong. The idea of the dot matrix is when you print a barcode for like a little PCB board, you don't want to print an entire sheet. Because an entire sheet, maybe you're taking the top row and you're throwing the rest away. So they wanted to just go up one line, and that's what a dot matrix did. And a Zebra printer. I hope I never have to look at another printer in terms of sending it special codes the rest of my life. It talks about the new line. Okay. Do while. I don't like do whiles. But here's an example one. Let's see, what is this doing? Looks like it's printing the numbers from 1 to 10. So you got your do statement here, and then you got your beginning curly bracket, and down here is your closing curly bracket. So it'll go through your loop one time no matter what. That's the idea of a do while. And it'll do this the first time, and then this plus plus will increase the value of counter, and then it'll do this check. So that's a concept of it, is you do it so it at least does it once. Now, have I showed you a lot of examples of printing the numbers 1 through 10 without using the do while? Well, let's see. Let's see. For int x equals 1. Of course, that's a do while. Let me do it with a while loop to be entirely fair. 2, 3. Int x equals 1. While x is less than or equal to 10. Printf %d space, space, and then I'll put in comma x, printf /n. There we go. Helps to actually increase it. Okay, let's try that again. My infinite loop I just wrote. Printf %d space x, x equals x plus 1. I just printed the numbers from 1 to 10. I didn't have to use a do while. Again, I set equal to 1. It's going to continue while x is less than or equal to 10. I print the value of x. I increase it by 1. So very simple. Like I indicated before, last time I think it was. Maybe it was this time. As you get old, you forget. If you have to use a do while, if you think you're forced to use it because there's no other way, it means you just don't know how to program a while loop. You can do 100% of them with a while loop. Okay, so I'm not going to go over that anymore because I don't like them. Now, break statements. Break statements are all right in this, your case statement, your switch. I have no problem with that. Where people use them, I think, incorrectly is something like this. Okay, so I'm going to x is equal to 0. Going to continue while x is less than 1,000 and increase x by 1. Now, if x times x is greater than 200, then I'm going to break. And I guess I ought to print something so you can see that it's actually doing something. And outside of here, printf all done /n. Now if I run that, it goes from 0 to 15 because 15 times 15, isn't that 225? Yeah. That's why that's greater than that. Oh, if it's greater than that, I printed it before that. Okay, so that's why I did that. But anyway, what I'm demonstrating here is you do not let the for loop finish its natural design. Its natural design is to go from 0 to 999. You can break out of a for loop, a while loop, ungracefully with that. I consider it poor programming practice. That means you didn't design your for loop or while loop correct in the first place. But they provide that capability. Used to be there was a go-to, and I don't know if this even has a go-to or not. Printf, let's see. Hi. Oh, that's horrible. Go to A. By. This is assuming I got the right syntax for, I never use this. Hi, I'm right here. So you notice it skipped. I did not do the by. Go to does not follow the standard design you did in your program. It's just free form, just go wherever you want. I could put B up here. And then down here, I could do a go to B. I'm shocked this actually is still in the language. And I just wrote an infinite loop. This was one of the programs I looked at Koch Industries when I was there. He had used go-tos all over the place. He had used single letter variables. And I could no more follow what in the world it was supposed to do than fly to the moon. And that's when I went back to my manager and said, I can't change this. I have any clue what it's doing. So yeah, go-tos, horrible. Same as break, never use them. Other people tell you they're probably good. Continue. Does it continue? I don't use that either. Skips the remaining statements in the body of that control. Oh, so continue skips the rest of the code for just that one iteration through the loop. I don't like that either. But okay, but it's there. Let's see. Break and continue statements, when used properly, perform faster than the corresponding structure techniques that we'll soon learn. I won't disagree with that. I just think they're bad programming. First, make your code simple and correct, then make it fast and small, but only if necessary. This all depends upon what you're doing. First, make your code simple and correct, then make it fast and small. In the Introduction to Digital Design class, which some of you going to Wichita State will have to take, whether you take it here or you take it to Wichita State, when you're working with circuits, what you'll find is that in one electronic device, you may have 10,000 circuits. And so if you first make the code simple and correct, that's fine. But if you don't do the fast part, you take that loss in speed times 10,000 circuits, and all of a sudden you got a lag in your electronic device that's not acceptable. So this you have to take with what are you going into? If you're going to program like David Hayes did for 13 years, yeah, who cares? The computers are fast and so forth. And, if you're going to design an electronic device, yeah, you have to pay a little bit more attention to this stuff. Here's our logical operators. Example of that. Input a number. Why am I having so much trouble with this spacing? 1, 2, 3. int num1. Scanf. %d. And then at num1. Here you can do a check if num1 is, see if I can screw this up, is less than -2, or num1 is greater than 5. Printf, the number was either less than -2 or greater than 5. If num1 is greater than -2 and num1 is less than 5, printf, the number was between -2 and 5. Okay, now let's run this, and I'll try 0. Number was between -2 and 5. Let's try -10. Number is either less than -2 or greater than 5. What this is doing is it comes here and checks this. If I put 0 in, is 0 less than -2? It's not less than -2, is it? That would be false. So that's false. The 2 pipe symbols there represents the OR. If I put 0 in for num1 here, and I ask myself, is 0 greater than 5? It isn't, is it? So this would be false. Now, if either one of these is true, then you do this printf. So that's what the OR does. If this is true, or if this is true, then I'll do this line of code. Since these were both false, that's why I didn't do this. But I came down to here. If I put 0 in here, 0 is greater than -2. So that would return true. And those 2 little ampersand is the AND. And if I put 0 in here, 0 is less than 5, so that's true. Now how this works is when you got the 2 ANDs here, both of these have to be true for this to print. So sometimes it's easier to combine them together using those. Let's see, is there anything else? Oh, this is really handy. I love this symbol right here. I've had programming circumstances like I had no clue how to change it to the opposite. So like if the degrees is less than -20 and the sky is sunny. This is a weird example, I know, but you run your program. Assuming I had all the rest of the code there. It's working opposite of what it should be doing. So instead of doing that if statement, it doesn't do it. What's the opposite of degrees is less than -20? Maybe greater than or equal to -20? Now, I don't remember how to do this, by the way, so this is probably not right. Sky is sunny. What's opposite of sky is sunny? Sky.
Cloudy.
Well, it could be nighttime, right?
Yeah, I guess.
It's hard to flip these to the opposite. It's hard. You could say sky is not sunny. And I think the AND here switches to 2 pipe symbols. I think. It's been a while since I took that class. Now, fantastic thing they added in for programming. We don't have to think that hard. If you put an exclamation in front of it, that'll flip it to the opposite. So if your code is working opposite of what it should be, just simply put an exclamation in front of it, and that'll flip it. You don't have to sit there and figure out how in the world to rewrite this. That's probably one of the best things I've run across in programming. Because I'd sit there and be scratching my head, and it's like, oh, how in the world do you get the opposite of that? And then I'd have to think about how would I redo the program, and you put an exclamation there, and in 5 seconds, you're up and running. Some people might argue that that's bad programming because you didn't know how to write it correct in the first place, and you just fudged it by putting an exclamation. But deal with that. There's talking more about logical operators. Truth table, if you have worked with those before. Logical operators. Performance tips. In expressions, use an operator to answer symbols, make the condition that's most likely to be false, leftmost condition. Okay. Here's a redo of the order of operations, what it does. So if you're real curious, this is be in a book, but this is the order that it does these in. If I'm not sure, again, I use parentheses around what I'm working with. Bool data type. You get old, that's important. Now, if I run this, that doesn't like something. Boolean alive. Is it uppercase? I thought I copied that from what they had. Look for the example. I don't have an example. Section FA.8 presents an example uses bool, true and false. No, that's how it's defined in the .h. Oh, I have to include the header. Standard bool.h. You know. Helps if I actually read. Okay. Now, let me get rid of that. I'm alive. Okay, so you have to include this header file. That's where it's defined at. And boolean is true or false, 1 or 0, yes or no. And so I declare a variable, a boolean, alive, and I set equal to true. And then I check if alive, and I don't have to do an equals equals here. The reason why is since this is true or false, this says, okay, if this is true, then I'm going to do this. So it's kind of a nice way to do flags. Instead of using that 1 like I did earlier, you know, for the switch example, the case, you could use boolean. And this tells you what it does. It replaces at runtime, it looks like it replaces true and false with 1 and 0. And boolean, what's it replace it with? Probably an integer if I had to guess. But that's boolean. We have already talked about the equals equals versus assignment operator. That'll catch you, cause you a lot of headaches. If alive equals true, like that. You can put it there. You can check to see if it's equal to true. You don't need to. But notice I put 1 equals, didn't I? Yeah. So if I change this to false, let's see what happens when I run it. It says I'm alive. Well, that doesn't make any sense because I just set it equal to false. I mean, I'm not alive. And here I'm checking if this is just an assignment. An assignment will always return 1 or true. So that's why you have to make sure when you do that that you have to put a 2 equals in there. I would consider a good programming language would catch that. I cannot think of a time when you'd ever want to put an assignment in an if statement or a while. It just wouldn't make any sense. But I'm sure they have an equal justification of why it's okay to do it. More about that. Using operator equals equals for assignment or using operator equals for equality is a logic error. Logic error means it runs, it just doesn't run right. Syntax error doesn't even get to the point it runs. Error preventing. When an equality expression has a variable and a constant, as in x equals 1, you may prefer to write it with the constant on the left and the variable name on the right. 1 equals x as protection against the logic error that occurs when you accidentally replace operator equals with equals. I don't ever do that. I hate that. Number on the left. I think everybody at some point develops their own little standard of how they like to program. After you write a program, text search it for every equals and check that it's used properly. Structured programming summary. I'm going to go with that. Okay. Secure C programming. This is really worthwhile to read if you want to program yours so somebody can't hack in and so forth. Figure 4.6, use the math library function POW, which calculates the value of its first argument, raises the power of its second argument, returns the result as a double value. As in used in that. Okay. Oh, scanf returns an integer, indicating whether the input operation was successful. So, if I was trying to program this correctly, printf input num1. We've been doing this. %d and then that. In printf, number was %d /n num1. So that's been our standard we've been using. Now if I run this, I put 3 in, returns number 3. If I run this, I put an XYZ. Comes back and tells me my number was 29. Doesn't make any sense, does it? Even more than that, people that are real clever with this can overload that and cause it perhaps to run something on your PC. So what they're indicating is that this actually returns an integer. So let's see if that's true. Let's say I got a result. And I'm going to say result equals scanf. I wonder what a good result is. Let me print out the result. Result is %d /n result. So if I run that, I put in 3. Looks like a good result says is 1. So 1 may indicate that everything's fine. Let me run this. XYZ, result is 0. Now I'd want to do some more checking before I officially programmed it, but that would imply that if my result is 0, they entered some garbage data. And so to prevent them from overloading the system and running a virus or taking control or whatever, I would do an if statement here. Let's say if result is equal to 1, that means it worked. And that's where I would then one more. Okay, so if I ran this now, let's see, put 3 in, comes back, result is 1, number is 3. Let's see. A computer hacker. Blah blah blah. Notice it didn't run my code, did it? Because I had the if statement here checking the result. So, like I say, this secure programming is good. If people actually paid attention to this, we wouldn't be having everything hacked into right and left. There was a whole book on how to do secure C programming, and it not only applied to C, but you could then extend it to other languages too. Okay, that's more about that. More about scanf. Yeah. Check its return value to ensure the number of inputs read match. Oh, the number of inputs read. So 0 means it didn't read any inputs. So what would be better probably to check is make sure that this is greater than or equal to 1. Like that. Because with a one scan statement, you can bring in multiple numbers. So. And it's still talking about how you need additional error checking besides, just what they could potentially put in wrong. What if they put in too big of a number? Let's see. That's got to be too big. Result is 1. It didn't give us a error in that regard, did it? So, Now I kind of went a little bit longer than I meant to. Usually been trying to stop at 9:15 to answer any questions you have. So I'll go ahead and stop the recording there.